Thanks so much for this opportunity. I'm going to talk about the work done at ETH in Reto Kludi's group. So this is in collaboration with many people, and it will be slightly related to Femke's talk at the beginning. So thanks so much, because maybe it will address some of the questions that came out in the chat in the meantime, but we only focus here on the transient timescales. So just to briefly motivate, like out of the CMIP6 models, nearly 1/3 of them have ECS values higher than 4.5, which was the upper bound of the IPCC fifth assessment likely range. And the reasons for those high ECS models are nicely discussed in Mark Zelinka and colleagues' paper in GRL. So instead of talking about why those models are high ECS, I'm going to talk about, is the future warming in those models likely? And what are the different methods or different lines of evidence of using observational constraints to constrain the future warming, as well as what are the implications for meeting the Paris Agreement targets and also the remaining carbon budgets associated with it. So similarly as the first talk, we're using the emergent constraint approach. And in order for this approach to remain valid, you need a verified mechanism and also possibly out of sample testing to test if it holds valid. So here we'll be using CMIP5 and CMIP6 data in a sense. And if you do have a mechanism behind the correlation, you could potentially use it to constrain future projections. So I'm going to briefly discuss the choices we made and how we justify that they make sense and why they hold valid in this type of emergent constraint. So we're plotting the warming trend for the 1981 to 2017 period, and then TCR values for those CMIP6 models on the vertical axis. So first of all, the trend was chosen such that this is sufficiently long period that the internal variability influence is small, but also changes in other forcings are small. So here you have individually forced simulations for the historical period for single forcing in CMIP6. And as you can see here, post 1980s, the trend in the aerosol forcing is nearly zero. So even though there is aerosol forcing present, the trend is nearly zero. And the trend in greenhouse gas forcing is very positive. So the historical warming is dominated by the greenhouse gas trend. And that's why we're able to constrain future warming, which is also mostly dominated here by greenhouse gases. Secondly, also during this period, the known modes of lower frequency variability, such as the Pacific and Atlantic variability, nearly cancel each other out. So actually, we consider two periods until 2014 and 2017. And in both cases, there is a cancellation between those low frequency variability modes, which again, helps the correlation to be strong, and it's not spurious or random, but it's actually driven by the forced signal. So here's an example of those CMIP6 models, and they are colored by the ECS values. So the dark models will be the high ECS models. And I'd like to emphasize, we're not constraining ECS, we're constraining TCR, but I'm interested in knowing if the high ECS models are kind of likely based on this analysis. So here is our observed warming trend in the gray boxes based on two observational data sets, the Cohen and Way, and then also the GISTEM. So both of them are nearly spatially complete or interpolated. And we estimated, so this gray box indicates uncertainty due to internal variability, which was estimated as a standard deviation across the large ensembles of initial conditions from the several large ensembles that were available, and we use the most conservative estimate. We also take into account separately the blending effect between the GSAT and the kind of blended temperature metric definition. And we also take into account structural uncertainty in observations, which was based on the 100-member Hartmut-4 estimate. So this kind of gray box, it's at 1 sigma and 2 sigma ranges. They account for those different sources of uncertainty in the observed warming trend. And we used also ordinary least squares regression. And from here, you can derive the constraint TCR value, which, as you can see here, like the high ECS models in dark red are less likely because they are outside, they're already warm too much for the present day conditions. And as a result, the constraint TCR, the likely range is the blue rectangle, which doesn't, like most of the high ECS models are excluded from that likely range. And if you add CMIP5 models to it, they are indicated by triangles. Similarly, like basically there's very little difference between my previous slide and this slide. The blue range is nearly the same. And you kind of basically add models in the middle and the lower end of the range. And just to address the question that came out in the chat, like regarding internal variability. So for our main analysis, we use the ensemble mean for how many members are available for each model. But if you consider each member separately, so this is CAN ESM5, for example, 50-member ensemble, I think you could use either weighted regression or bootstrap prediction error. In either case, the upper end of TCR is always below 2, which is consistent with the previous one. The lower end, we don't constrain the lower end well, but like the upper end is below 2 in both cases, as was in the main case where we take the multi-model ensemble mean. So I think all these internal variability constraints, both from the model internal variability as well as the low frequency variability, like they have very little difference in using this type of method. So this is kind of the results for TCR. The gray ones would be the unconstrained likely range and the 5 to 95% interval. For CMIP6 alone, CMIP5 alone, and the joint sample. In each case, the blue bar indicates the constraint result, and the median value is always lower, and it's consistent with the AR5 and also briefly consistent with the Sherwood estimate for TCR. So as I mentioned, like we're looking only at the transient timescales. We didn't look at the equilibrium timescales because of all this nonlinearity is very nicely described by Femke in the first talk. So just to kind of put it in context of other studies, these are generally consistent results. So all those studies show that high CS models show too much warming, and their projections are less likely because they warm too much. So I'm also briefly going to talk about the regional contribution, because as we mentioned, the emergent constraint needs to arise due to a known mechanism. So in order to see that this is not a spurious correlation, we looked also at the spatial fingerprint pattern. So for each model map of warming, we removed the global mean trend from each grid cell in a given model. And then we projected this kind of model spatial trend pattern with no global mean onto this multi-model fingerprint. And this is what you can see, this pattern covariance as a function of TCR on this plot as well. The correlation is a little lower, but it's still quite strong. And you can see, well, the observational uncertainty is larger because on the regional scale, you have larger internal variability. But nevertheless, again, the high CS models are on the upper end of the range. And here is the kind of fingerprint picture, so you can see which regions contribute to this correlation. And as expected, this will be the polar amplification region. You can see the land-sea contrast and warming in the Southern Ocean. So there are physical reasons why this correlation would exist, and this is not due to spurious or random correlation. And again, the noise due to internal variability, if anything, would just destroy this correlation, but we still see it that this is due to forced pattern and not due to randomness. So what are the implications of this type of correlation for future warming? So here I'm looking, we look at different SSP scenarios, but I'm going to show you the SSP 1 to 6, which is the ambitious mitigation scenario, very ambitious mitigation with aims to reaching the Paris Agreement target of warming below 2 degrees. And as you can see here for the raw sample of CMIP6 models, if we look at the 2-degree target, all the most of the high CS models in dark red here are above 2 degrees. We can use the same method. So this is exactly the same observational constraint as before. And we see there's strong correlation. So we can use it to constrain future warming in SSP scenario. And as a result, the blue rectangle is contained within this kind of Paris Agreement target below 2 degrees. And the median by the end of the century is also consistent with the Paris Agreement target. So we can see that like the high CS models warm too much, and therefore I would say their response is less likely. And next, I'm going to briefly talk about alternative method that was also used by the ETH group. And there's another paper also using this method based on the warming signal alone, but I'm going to focus on the paper I'm more familiar with from Lukas Brunner and colleagues. And they, the main difference, the main difference here is that they use different observational, different variables. So use both spatial warming and sea level pressure, also spatial pattern, and then they produce weights for each model. So as you can see, this is the raw results for the 2 different SSP scenarios and TCR, and then constrained ones. So again, the main conclusion is the median is below. So by using different ways of observational constraint, you end up with lower median and lower upper range than if using the raw CMIP6. And this is again consistent with the previous studies I showed before. So the very final part, I wanted to show correlation between TCR and TCRE. So TCRE is this metric for carbon budgets. And similarly, as you would expect, high CS models happen to have high TCRE because there's a strong TCR is the main determinant of TCRE, and this would be outside of the observational constraint and also outside of the observationally constrained TCRE range from an earlier study. Therefore, if you calculate carbon budgets from CMIP6 models alone or from emulators tuned to CMIP6 models, of course, you will end up with lower carbon budget, but I would again argue this is not consistent with the observations, and I wouldn't recommend using like those models as a line of evidence that the remaining budget is lower, because I don't think that's the case. And then the recommended approach is to use multiple lines of evidence, like the special report did with the distribution of TCRE, or the upcoming paper that has observationally constrained distribution of TCRE, and then use kind of the segmented approach introduced by Yuri Rogel last year and in the special report, where each component is assessed separately, and that way you get better assessment of uncertainty in the remaining budget. So just to conclude, generally the multi-model CMIP6 global mean will be biased high due to those high ECS models. If one way to address it would be, for example, using the time shift approach, like pattern scaling approaches suggested earlier. And thanks so much for your attention.